So in this lecture, we will cover a special class of problems in kinematics which are related to the approach velocity. So watch this video to the end, especially the tricky problems in the end, which look tricky, but if you know the how to tackle this problem, it becomes easy. And the issue with these kind of problems is that if you do not know these problems in ahead, at least a little bit of this, it gets hard to do it in the exam. So let's say, what is an approach velocity? Its approach velocity is related to the relative velocity, so we'll understand it with an example. Let us say we have 2 points A and B here, and this one, they are on the x-axis and they are moving in one dimension, and this one is moving with a velocity of, let's say, 4 meters per second, and then B is moving in this direction with a velocity of 6 meters per second. I'll make it smaller to show that this is a smaller velocity and this is a little longer to show that it's a higher velocity. And let us say they are separated at a distance of 100 meters between each other. So what happens? If you observe them after 1 second, then this will have moved to a distance of 4 meters here, and this will have moved a distance of 10 meters, 6 meters here. So the separation between them after 1 second reduces to 90 meters. That means in 1 second they approach to each other with a velocity of with a distance of 10 meters. So the velocity of approach is 10 meters per second. So velocity of approach is equal to 6 meters per second plus 4 meters per second, that is 10 meters per second. So if two particles are moving towards each other, then their approach velocity will be just the sum of these two velocities. On the other hand, if I take the same problem and present it like this, let us say this is a thief. It is trying to run away at the speed of 4 meters per second, and this police is trying to catch it with and it is at the police is moving a little faster at 6 meters per second, because if it does not, it will never be able to catch the thief. Now what happens after let's say 1 second? After 1 second, this has moved a distance of 6 meters and this has moved a distance of 4 meters. Now the separation between them has reduced to 98. What does that mean? In 1 second, the police has approached the thief a distance of 2 meters. So the approach velocity in this case is equal to 6 meters per second minus 4 meters per second, or this is equal to 2 meters per second. This is just the difference of these two velocities. And if this velocity is 6 and this velocity is 4, they will never meet each other. And that is the one thing you need to keep in mind, whether they will be able to, they will converge or they will not converge, depending upon this approach velocity makes the distance go smaller or go larger. So we use these concepts to move further and to solve some difficult problems. But before we do that, let's say what happens. Let's say A is here and B is here, and B is moving not in this line, but let's say it makes an angle, some amount of angle theta, and then B is moving with the velocity v and A is moving with the velocity u, like this. In this case, what is the approach velocity? The velocity with which A is approaching B. That's one thing we need to find out. So what we do is we resolve this v into two parts. One, this is v cos theta, and this vertical component is v sin theta. So the velocity with which A approaches B along this direction, along this axial direction, is going to be u minus v cos theta. And this velocity will be called the radial component, the velocity with which it's trying to run away in the perpendicular direction. And let's say if this velocity u is greater than v cos theta, at some point of time it will be able to catch up in the x-axis direction, although it will be gone in the y-axis direction. But if we match their x coordinate, it will be able to match this. But if A is less than v cos theta, it will never be on the x-axis, it will never be able to catch this up. So this is the concept. This concept is we will use in next few problems that we will present to you. So I will not write the whole problem, just explain to you and then we will solve it. We are given a triangle, this triangle A, B and C. And what's happening is there are three particles on these points and they try to move. A is trying to move towards B with a velocity v. B is trying to move towards C with a velocity v, and C is trying to move towards A with a velocity v. And this triangle is a equilateral triangle with each side equal to D. We are trying to find out when this A point will meet B. So initially the problem looks a little tricky, and that's why I say if you have understood it, then you can solve all such. If you have solved one such problem, you will be able to solve all such problems. So let's say what is happening. After a little bit of time, this point A is trying to match B, while B has tried to move at C. So let's say B have moved here. Now the A will start pointing this direction B. And C in the meantime has moved here and the A has moved like here. So they will again be in a kind of a triangle, something like this. A moves in, B moves here, C moves here, and then they will again move something like this, and they will again keep moving like this. So this whole thing, they will start traversing a path and they will eventually converge it at the center of this triangle. This is what is happening, and every point of time this is still a triangle. When they are moved here, there is still a triangle. Here is still a triangle. At every point of this movement, they still keep a triangle, they form a triangle, and that is an equilateral triangle. Now we have understood this. All we need to do is find the approach velocity, the velocity with which any point A is approaching towards B. And for this, you need to notice that this point A is approaching it with a velocity v here. So along this line, what is the approach velocity? This will be this velocity. This velocity is v, but this velocity, the b is trying to move here. But if you clearly look at this velocity has two components. Let's say one component here, another component perpendicular to it. And with its component along this line, this tries to come towards C. This guy is also trying to come towards A. So they are trying to come towards each other faster than we are thinking. So what we do is, we do this angle. If this angle, the component of the point B along this is v cos theta. And therefore, the approach velocity will be equal to v, this one, This is the velocity with which A is trying towards B, and V cos theta is the velocity with which it's trying to come towards A. So this is V cos 60, and cos 60 is 1 by 2. So this is V 1 plus 1 by 2, or this will be equal to 3V by 2. And with this velocity, it needs to cover a distance of D. Now, during the whole path, it may be following some trajectory, but it eventually, at every point, with its radial velocity, it will be moving in its radial direction. But every point of time, it has to eventually cover this distance. So that this time taken is simply the approach distance divided by approach velocity. The approach distance is d and approach velocity is 3v by 2, so the answer is 2d by 3v. The one thing you need to make sure is that we are able to solve this problem because there was a symmetry in the problem, certain kind of symmetry which ensured that the particles are able to converge at some point of time. In all approach velocity problem, you will be doing like this. We will move on to do another variation of this problem. And now that you know the trick, I will suggest that once you know what the problem is, you'll try to understand this problem. Let's say we are given a hexagon. The hexagon has a side D, and there are again the particles A, B, C, D, E, and F. A is moving towards B, B is moving towards C, C is moving towards D, D is moving towards E, E is moving towards F, and F is moving towards C. We need to find out the time taken when A meets B or when they all meet together. So you pause this video, try to solve. The one thing you need to make sure that the two particles in the last problem, I will give you a hint. If you don't want the hint, you stop it here. If you want the hint, don't stop and listen the hint and then try again. The hint is, in the last problem, the two had approach velocity such that they were trying to come towards each other. In this problem, the approach velocities are such that one is trying to come towards this, the other is trying to run away from it. So pause this video and try to do that and come back. Let's try to solve now. The first thing we are trying to know is the angle. This angle is same as if you join this triangle inside and you do some simple geometry, you will find that this angle is 60 degrees. And what is happening in this scenario? The same as other. A tries to B, but B tries to move here, so B comes here, and A maybe comes here, C comes here, D comes here, E comes here, F comes here. The whole thing becomes like that, but there is still along the side of another regular hexagon. And then the whole thing keeps moving like this, but at any point of time, all the particles are along the hexagon. Which means that at all point of time, at every point of time, the relative positions of A and B are same, which is B is moving at an angle 60 degree with respect to A. Which means that A and B always have the same approach velocity all along the path. So what is the approach velocity in this instant of time? A is moving with velocity V and BC, along with BC, this is moving with the velocity v. So the component of this particle B along this is going to be v cos theta in this direction. So A is moving with velocity v, but B is trying to run away with the velocity v cos 60 degree. So the approach velocity is going to be v minus v cos 60 degree, which means v 1 minus cos 60 is 1 by 2, because sine it is same as sine 30. Sine 30 is 1 by 2. So this is v by 2. At every point of time, no matter what configuration, where we are in this hexagon, at every point of time, it is always on a hexagon. The B is always making an angle 60 degree with respect to the direction of A, and therefore this approach velocity is always v by 2, and the approach distance is d. So the time taken, t, will be equal to this, the approach distance d divided by the approach velocity v by 2, or this will be equal to 2d upon v. So this is the solution of this hexagon problem. We can also have some more variations of this problem, and I will suggest that you try this. I'll write down two more problems for you, and then you need to again pause the problem and then solve for this. The next one will be easier because you have already done that, and instead of the hexagon I have not taken a octagon, and in this octagon there are particles A, B, C, D, E, F, G, H, and the particles A, B, C, D, E, F, G, H, they are moving with the velocity u, and the side of this hexagon, let's say, is D. You need to find out the time it will take for A to meet B, or for all particles to converge and meet. That is your exercise number 1. Exercise number 2 is, let us say we have 4 particles A, B, C, D. This is the square of side D, and A is moving towards D with a speed u, with a velocity u in this direction. B is moving towards C with a velocity u, and so on and so forth. See, in the same, this also you have to assume that all the particles are moving towards the other one like this. And you need to find out what is the time taken for them to converge and meet at the center of this square. So this one, I hope it should be very simple. So just pause it and try to do this. If not, but the first thing you need a hint. The first hint is that this angle theta is equal to 45 degree. So once you have solved this, again the approach velocity here is, this is trying to move with the velocity v towards B, but B is trying to run away from A with the velocity u cos 45 degree, which is a component of this velocity along this direction. So the relative velocity is u minus u cos 45 degree, which will be u into 1 minus 1 upon the square root of 2. This is the approach velocity of A with A. It is the velocity with which A is trying to approach towards B. And now the distance between them is d. If let's say this is d, the time taken to reach towards B will be this approach distance d divided by approach velocity u, 1 minus 1 upon the square root of 2. If you want, you can simplify it a little bit, but it's not really required. T square root of 2 divided by square root of 2 minus 1, and this we can write d square root of 2 multiplied by square root of 2 plus 1 top and bottom, square root of 2 plus 1, and this can become square root of 2 minus 1. A square minus b square is 2 minus 1 is 1. So this you can write d 2 plus square root of 2. Just a little simplified version of this. Coming back to question number, this question, the square, it is actually much simpler than this. A is trying to approach towards B with a velocity u, but u is not trying to run away or come closer to it because it's perpendicular. So A is radially moving away, but there is no, it has no component along this axis. So this approach velocity is equal to u, and the approach distance is equal to d. The time taken will be equal to distance d divided by velocity u. What is actually happening? A moves, B moves something like this, C moves something like this, D moves something like this, A moves something like this. So they become something, you can think of that like this. Again they are forming a square, and every time there is a square, and because every time they form a square, every time the approach velocity still remains the same, which means B is always perpendicular to A. It has no component along the side where A moves, and therefore we can apply this formula, time of approach velocity, time equal to approach distance divided by approach velocity. So this is all about the approach velocity and its concept. You need to start with the relative velocity. Relative velocity becomes an approach velocity if the two sides are converging or in some way, and this is a thing you can apply for other similar problems.